Welcome to this explainer. Today, we are tearing down one of the absolute highest stakes challenges in modern automotive engineering. I want you to picture an electric vehicle motor just screaming at 12,000 RPM. Right at the very center of that mechanical hurricane is the encoder. You can really think of the encoder as the literal heartbeat of the EV motor. It's this vital sensory organ that tells the motor controller exactly where the rotor is, at what angle, and at what speed, thousands of times a second. Now, when it works perfectly, you get smooth, silent, blistering acceleration. But what happens when that heartbeat skips? Today, we're going to unpack the underlying physics of encoder anomalies and the totally extreme engineering required to survive a pulse loss.
So what exactly happens when an EV motor spinning at 12,000 RPM just loses its pulse? Well, the physical reality is violent. If that signal drops, even for just a few measly microseconds, the field-oriented control, or FOC, algorithm instantly loses its spatial orientation. The stator's magnetic field falls completely out of sync with the spinning rotor. So instead of driving the vehicle forward, the magnetic forces suddenly start fighting each other. This results in catastrophic torque loss and incredibly violent torque ripples. In a fraction of a second, a smooth highway ride turns into a chaotic, potentially uncontrollable mechanical shock to the entire drivetrain. That right there is the disease we have to cure.
And to cure it, we are using a strict defense-in-depth approach. We're going to break this down methodically. Number 1, fault root cause analysis. 2, co-diagnostics and fallback. 3, DFMEA key design preventions. 4, PFMEA critical process controls. And finally, 5, DVP&R production validation.
All right, let's jump right into Section 1, Fault Root Cause Analysis, the pathology of failure.
To fix this problem, we first have to understand the incredibly hostile physical environment inside a motor. I mean, it's an environment that actively wants to tear sensors apart. The conditions inside a dual motor casing are an absolute nightmare for signal integrity. We're talking about extreme heat, intense vibration, and severe electromagnetic interference all conspiring at the exact same time. First, the mechanical and thermal stress. High-frequency random vibrations between 100 and 1,000 hertz can literally crack optical glass. Then you have extreme heat, pushing well past 130 degrees Celsius, which degrades electronics and demagnetizes materials. On top of that, electromagnetic crosstalk. The silicon carbide MOSFETs are switching at incredibly high speeds, creating these huge voltage spikes that can trigger false overspeed alarms. And inside the processing chips, if the clock domains aren't perfectly synchronized, you get phase sliding and metastability. Basically, the chips lose their sense of time and start hallucinating data. And finally, there's frettingware, which is literally grinding down the physical metal connections. Because of this environment, engineers are forced into a really brutal trade-off between optical and magnetic encoders. And honestly, neither is perfect. On side A, you've got optical encoders. They rely on highly precise glass encoder discs and LEDs. But under massive temperature swings, from -40 to positive 150 degrees Celsius, microstresses form. The glass can literally shatter, and the LED's luminous intensity permanently degrades, giving you massive pulse distortion. Now in side B, magnetic encoders are cheaper and smaller, but they have their own kryptonite. If you push the motor load hard enough to break 130 degrees Celsius, the magnetic targets undergo irreversible thermal demagnetization. The magnetic signal just melts away until the processor can't read it anymore. Plus, they are highly vulnerable to that high-frequency EMI noise generated by the motor's power switches.
But wait, it gets crazier. Beyond the sensor itself, the literal plug connecting it to the computer is under attack. Let's talk about frettingware. The low-voltage signal connector is constantly vibrating. We are talking about relative sliding on a microscopic scale, under 5 micrometers. These microvibrations slowly scrape off the protective tin layer on the pins, exposing the oxygen-free copper base beneath it. That copper rapidly oxidizes, stacking up this microscopic insulating oxide debris. Suddenly, a pristine connection that had less than 5 milliohms of resistance spikes to over 100 milliohms. Bam! You get microsecond-level signal interruptions that instantly kill motor torque.
Which brings us to Section 2, co-diagnostics and fallback, the immune response. Look, physics basically dictates that these hardware failures will happen eventually, so the system needs an immediate immune response to detect and react before the driver even realizes something went wrong. Enter the doer-checker architecture, which is a core component of the ASIL D safety standard. Think of this as having an internal auditor, literally looking over the shoulder of the main processor. The primary core, the doer, is running the highly optimized dynamic field-oriented control loop.
But right next to it, the secondary safety core, the checker, is running an entirely independent virtual physics model. It uses flux conservation and real-time resistance tracking, known as an MRS plausibility model. It constantly compares what the physical encoder is reporting against its own virtual mathematical prediction. If the physical sensor and the virtual model disagree by more than a calibrated limit, let's say 10 degrees, the safety core realizes the physical encoder is compromised. In under 100 microseconds, it bypasses the main code entirely and directly kills the pulse width modulation signals.
Now, if the vehicle was moving at high speeds, say above 80 kilometers per hour, or motor speeds over 7,200 RPM, you can't just flip an off switch. If you just open the circuit, that spinning motor becomes an uncontrolled generator, and the back electromotive force will blow up your electronics. Instead, the system executes a lightning-fast stepwise active short circuit. Step 1, for exactly 1.5 milliseconds, the hardware forces a two-phase short circuit. This absorbs and suppresses the massive transient demagnetization current. Step 2, it instantly transitions into a three-phase short low-side configuration. This acts like an electromagnetic brake, clamping the DC bus voltage safely below 720 volts, ensuring those expensive silicon carbide MOSFETs don't explode on you.
And here is the kicker. 60 milliseconds. Under the ASIL D safety architecture, 60 milliseconds is the absolute maximum fault-tolerant time interval, or FTTI. From the exact microsecond a physical pin loses contact due to fretting wear, the system has to filter out the noise, realize it's a real failure, cross-reference the dual-core lockstep, and execute that complex active short-circuit fallback. If it takes 61 milliseconds, the torque surge could cause the vehicle to lose control. Everything we just discussed has to happen in 60 milliseconds flat. For some perspective, a literal blink of a human eye takes about 300 milliseconds. This motor has to save itself 5 times faster than you can blink. Moving upstream, we hit Section 3, DFMEA Key Design Preventions. The vaccine. Now, relying entirely on a microsecond emergency response, that's living a bit too dangerously. We have to move upstream to the blueprint phase, designing vaccines to eliminate these pathways to failure before a prototype is ever even built. One of the most common causes of signal failure is thermal drift in the filtering capacitors. When temperatures swing wildly, cheap capacitors actually change their electrical properties, which warps the analog signal. So the mandate here is 0 plus or minus 30 parts per million per degree Celsius. Designers are absolutely forced to use Class 1 C0G multilayer ceramic capacitors in the low-pass filters. These specific components have virtually zero thermal drift across massive temperature swings, from negative 55 all the way to positive 125 degrees Celsius. Plus, they don't have a piezoelectric effect, meaning physical vibrations won't generate false electrical noise. By locking this into the bill of materials, engineers physically eliminate thermal mismatch noise right at the source. We also have the vaccinate against electromagnetic interference, and the mandate here is completely non-negotiable. 360 degrees symmetrical shielding with under 10 milliohms of grounding resistance. Because those silicon carbide switches are firing off massive high-frequency voltage spikes, any gap in shielding lets that noise bleed straight into the encoder's signal. The encoder wire harness has to use high-density twisted shielded cables with over 85% braid coverage. And check out this warning. Pigtail grounding is strictly prohibited. Seriously, a single-wire pigtail acts like a giant antenna for high-frequency noise. You must use 360-degree metal backshells pressed directly to the casing ground to block that violent common mode noise. Okay, let's take this to the factory floor. Section 4, PFMEA, Critical Process Controls, Factory Safeguards. Because, let's be real, a perfect design on a computer doesn't mean a thing if it's assembled poorly on the factory floor. Remember that fretting wear we talked about earlier? The micro vibrations destroying the copper pins? Well, here is the factory-level mistake-proofing, or poka-yoke, safeguard against it. Step 1, an automated machine injects a hyper-precise micro-drop of automotive-grade floral silicone grease right into the terminal. But how do we know the machine didn't miss? Step 2, that grease actually contains a UV fluorescent tracer. An automated optical inspection system flashes a UV light, literally like a CSI crime scene investigation for your motor, to verify 100% grease coverage before the part is even allowed to move down the line. Step 3, during the actual wire crimping, sensors monitor the force displacement curve in real time. If the cold weld mechanical profile looks even slightly off, the equipment physically locks down.
This creates an absolute web of assembly accountability. Every single shift begins with destructive pull force testing, making sure those crimps can hold at least 50 newtons. For the high-current busbar bolts, optical character recognition cameras verify that the fasteners have the required phosphate coating. Then, servo drivers tighten them while analyzing real-time torque angle curves. If the friction coefficient shifts at all, the assembly line halts, ensuring physical contact resistance remains under 5 milliohms. Finally, at the end of the line, the manufacturing execution system forces an automated rotor offset learning process. The measured back electromotive force must perfectly match the excitation current phase angle, and this data is locked into the cloud. If it doesn't match perfectly, the system just flat out refuses to print a passing label.
Finally, the last line of defense, Section 5, DVP&R production validation, extreme stress testing. So we've designed the perfect system and we built it flawlessly. Now, we enter the extreme testing phase, where engineers deliberately try to break the system in brutal ways to prove it literally can't be broken. It's the ultimate gauntlet. First, they subject the system to 500 hours of brutal, random vibration alongside extreme thermal shocks. The acceptance criteria? 0. Absolutely 0 signal drops lasting longer than a single microsecond, and no demagnetization whatsoever. Next, on a dynamometer running at deep thermal saturation, they inject a violent 20,000 RPM per second squared acceleration shock whilst manually cutting the sensor wires. The software's sensorless observer must seamlessly take over control in under 5 milliseconds with minimal torque ripple. And finally, the boss fight. At a full load of 12,000 RPM, engineers intentionally short-circuit the encoder signals. As we covered, the safety management unit must hit that FTTI limit, diagnose the fault, and flawlessly execute the active short circuit, clamping the bus under 720 volts without blowing a single power switch.
The engineering required to achieve ASIL D functional safety is truly a marvel of modern problem solving. It's this perfect blend of physics, material science, software, and rigid manufacturing discipline. And honestly, it leaves us with an incredibly important question for anyone out there working on complex systems. Is your team's software debounce window truly optimized for the next transient pulse loss? Have you accounted for every single microsecond in your fault-tolerant time interval? Because taking a defense-in-depth approach isn't just about passing a certification. It's about guaranteeing reliability when the actual laws of physics are working against you. Thank you so much for joining me on this explainer, and keep questioning how your systems fail.